Okay, now we're on. Kinetics. Here, there are many things we could point to, but I decided to pull up the airbag. Sodium azide. What you need here is you need a really quick reaction. Very quick. As a matter of fact, I started doing some calculations here, and I wondered if this was quick enough. It said in 40 milliseconds this bag is going to deploy. But you know, at 60 miles an hour, you're traveling 880 feet per second. 880 feet per second. So is 40 milliseconds fast enough? Obviously it is. Oh, it either is, or this number is not right. It's more like a tenth of a millisecond or something like that. But how, you only got about 2 feet to travel there before you're going to hit the steering wheel, and that thing's going to deploy. And this thing decomposes into nitrogen gas very quickly. So it blasts that open with nitrogen gas and then deflates, and it doesn't suffocate you, all that sort of thing. So pretty wild, but pretty dramatic from all the other kind of stuff you hear about airbags. Don't drive recklessly and think, oh, my airbag's going to take care of me. Well, it also may break your nose and do some other things. I mean, it's not as bad as not having the airbag, but it is a dramatic event to actually deploy an airbag. All right, so kinetics. Study the rates of chemical reactions. The reaction rate is the increase in concentration of the product per unit time, or the decrease in concentration of reactant. And this is probably what we will talk about the most in terms of a reaction rate, because a whole lot of times we're going to be looking at, here is sodium azide, reactant, and so what is reaction rate? We'll look at it, it would be looked at in terms of the disappearance of the reactant as a function of time. And then reaction mechanism, series of molecular steps by which a reaction occurs. Okay, thermodynamics. This is going to be something for us to think about as we go through this chapter. Just this relationship here. So far, thermodynamics has been able to explain just about everything. We've been able to mathematically figure something out before we actually even go in the lab to get any data. We kind of figure out how much heat is going to come out of this reaction and things of that. But here's kinetics. Kinetics determines how quickly a reaction will occur. Thermodynamics doesn't tell us that. So here is a place where you actually have to have empirical data. You have to actually go in and do an experiment. You can't just sit there and theorize. At least we'll see as we get through the end of this chapter. But you can't just sit there and theorize whether this is going to be fast or slow, or this is going to be fast or slow. You have to rely on experience, and we kind of know that diamonds are pretty durable. Just don't leave them, they stay in a house fire, they're going to burn. The diamonds are going to burn eventually. But this is a very slow reaction, but at a certain temperature it'll go. This is a very fast reaction, acids and bases neutralizing one another. Bam, just like that. Rate of reaction, change in the amount of reactants per unit time. That's it, that's what we'll focus on. Units are, they're not going to always be, the rate we're basically, the rate we're usually looking at the decrease in molarity, change in molarity as a function of time, seconds, minutes, hours, but usually you'll see seconds in there. So the brackets, molar concentration rate is the change in A as a function of time. And here it is, negative that this is going to be decreasing. A is going to be decreasing with time as it converts to B. B has a positive, B is going to be increasing as A decomposes or reacts to form B. All right, and in this particular case, assuming we've got the coefficients are 1 for A and 1 for B, there's nothing in front of this rate. The rate of the formation of B is, or the rate of decrease of A with respect to time is equal to, but opposite in sign, of the rate of formation of B with respect to time. All right? So, Dominic, we're just kind of reviewing your principles to kinetics and warming up to this topic of kinetics as we get into chapter 20. So there's the beginning. All you have is A. All you have is A, and A is diminishing. B is being produced, and so the decrease in the molar concentration of A with time is equal to the appearance of the molar concentration of B with time. There's just a 1-to-1 ratio there, a 1-to-1 correspondence between A and B. Example, decomposition of hydrogen peroxide. We're just looking at, here's time in hours. Here's the concentration of the hydrogen peroxide. And so here's the change in time every 6 hours. And there's the diminishing concentration, rate of decomposition of the hydrogen peroxide. So we could write, what is that rate? What is the rate with which hydrogen peroxide is? So the initial concentration minus the final concentration divided by the time, and we got a rate. All right, so a lot of times we look at the initial rate. What is the initial rate of that reaction, the start of the reaction? But we can take tangents off of that curve and actually get an instantaneous rate. What is the instantaneous rate at any point along this curve? And here it is, two hydrogen peroxides producing 2 water molecules and oxygen. All right, those of you in biochem probably know this, but and also if you gargle with hydrogen peroxide, you notice how it foams up in your mouth?
I've tried it.
The bacteria in your mouth is converting the hydrogen peroxide to water and oxygen. And it foams. It's producing oxygen. You can actually use hydrogen peroxide with a little bit of yeast. You can put that into a flask and you have an oxygen generator. Just take hydrogen peroxide and yeast. The bacteria in the yeast will immediately start catalyzing the hydrogen peroxide to water and oxygen, and you've got an oxygen generator. So it happens pretty fast. In your body, you have the enzyme catalase, which is doing that. Okay. Let's consider a hypothetical reaction where the lowercase letters are the coefficients, the uppercase letters are the compounds in the reaction. Elements or compounds. So you have this reaction, and you could express that reaction You could express the rate of that reaction in 4 different ways. You could express it with respect to A. What is the rate of that reaction in terms of the disappearance of A? It's minus 1 over the coefficient times delta A over delta T. Or B, it's equal to minus 1 over the coefficient of the change in B with respect to time, or plus 1 over C. Should have had that reaction up there again, etc. So the reaction has one rate. Okay, it has one rate. You could express it in terms of any compound in the reaction. You say with respect to hydrogen peroxide, it's going this fast. With respect to oxygen, it's going this fast. With the generation of water, it's going this fast. So those come into those to play there. And we're just talking rate. So you can write it in terms of any one of the compounds or elements, any reactants or products in the reaction. Okay, so the rate of a simple one-step reaction is directly proportional to the concentration of the reacting substance. It's going to be proportional to, so if we have A going to be B plus C, the rate is going to be proportional to the rate, the concentration of A to begin with. And so this is moles per liter. K is the specific rate constant. And this is important. This is what we'll be looking at a lot in this chapter. This is K. What is this rate constant? So a kineticist examines the reaction they want to study and tries to figure out, how can I monitor this reaction? And so it has to do, here for example, bromine reacting with formic acid to form bromide and carbon dioxide. It would look pretty much similar. This would look very similar if you had bromine and hexane, for example. Hexane and alkane, and you have a slow reaction in the presence of UV light, and you're looking at a color change. So you can take a simple calorimeter and set it on that wavelength of color, and you could actually measure and quantify the disappearance of the bromine with time, and you get your data. With the hydrogen peroxide, you could actually look at, if you enclosed it in a container, you could look at the increase in pressure as oxygen is being formed. You just kind of watch the pressure going up, and something like that. Or you could bubble the oxygen into a container and look at the volume of oxygen being produced as a measure of the rate of that reaction. So a kineticist just has to examine the reaction and decide, what can I get my hands on here and measure.
Could you also measure that by pH?
Which, this one, yeah, you could use a pH meter in this case. Maybe not with the bromine with an alkane, but here bromine with formic acid. Let's see, what are you getting here? CO2. Plus 2 hydrogens. Okay, you're forming hydrogen bromide. It's going to start out acidic.
Yeah.
Somewhat acidic, so that you could probably dig into it that way. All right, just simply writing this out. Here's change in negative. The change in the bromine concentration is a function of time. And there's time, there's your bromine concentration. At any point in here, you could get your bromine initial is staying the same. So your T initial is T0. We're going to be referring to that as T0, or that's going to go away later, and we're going to just be we're going to realize that the initial temperature is times 0, and so we're going to start shifting over to just look at T, the amount of time. Okay, here this is based on the previous slide's data. Did you get one of these, Ryan? You got one? Okay. This is based on the initial slide's data, and just kind of worth just glancing at it. Here is the instantaneous rate. So this is a tangent off of that line. And here is the overall rate, based on initial concentration, final concentration. What is the overall rate of that reaction? And yeah, here's your K. Well, I'm sorry, that is actually calculating the K for the reaction. So K is a constant. K is a constant at a particular temperature. We'll look later in this chapter at how does the rate constant vary with temperature. So you do have to specify this is the rate constant for this reaction at this temperature. It is a constant, but not for every temperature. You increase temperature, you increase rate. Here's another one. Here's one with some specific coefficients. Methane and oxygen for producing carbon dioxide and water. There's the balanced equation. So there is a particular rate for that reaction. In terms of methane, it's the disappearance of methane with respect to time, which is equal to negative one half the disappearance of the oxygen concentration with respect to time. Okay, but basically what we're saying is the rate of disappearance of oxygen is 2 times the rate of the disappearance of the methane. The oxygen is going to disappear twice as fast as the methane in moles per second. All right, so those coefficients come in to those, and you get these four relationships that they're equal. Here's 2 hydrogens plus 1 oxygen forms 2 waters. Express the rate in terms of changes in hydrogen, oxygen, and water. So the rate equals negative 1/2 the concentration of hydrogen with respect to time. It equals negative 1 times the disappearance of oxygen. And with respect to water, it's positive delta respect to time. We'll be moving this over to differentials as we move on. When oxygen is decreasing at 0.23 moles per liter per second, at what rate is hydrogen increasing? So, so the hydrogen is going to be double that rate. If we take this equal to that, is basically saying the rate of the water is going to be 2 times the rate of the oxygen. .46 molar per second. Okay, so we end up with this rate equation, simple equation, rate equals K times the change in the concentration of A. If the initial concentration of A is doubled, the initial rate of the reaction is doubled. Now, we're writing out a rate law here, and what we haven't talked about yet is the order of that reaction. But if that was a first order reaction. Yeah, Grant?
Can we go back to the last slide and finish writing? I'll take my try to so you can do that.
Okay, here we'll start talking about order of reaction in just a second, but assuming this was a first order reaction, first order in the concentration of A, first order in A, if you double the concentration of A, you're going to double the rate. The rate will double. If you have the concentration of A, you'll have the rate. And going back to the previous chapter, I mean, to just tie it a little bit to chapter 19, we talked about particles colliding and reactions being the result of particles colliding. So concentration is a big factor in reaction rates. You raise the concentration, you raise the number of things there that can collide or decompose, break apart, whatever. So concentration is a big factor in reaction rates, as well as other factors are. Concentration, catalysts, temperature. There are some really key variables in reactions. If more than one reactant molecule appears in the equation for a one-step reaction, we can experimentally determine that the reaction rate is proportional to the molar concentration of the reactant raised to the power of the number of molecules involved in the reaction. Rate proportional to the concentration of X to some power A. Now, what we'll see as we go on here, this coefficient and this coefficient are not necessarily the same. In some cases, coincidentally, it works out that way, but in most cases, that isn't necessarily the case. It doesn't just follow that because stoichiometrically 2x yields y and z means that the reaction is going to be second order in X. That is not given, all right? Whether the order of a reaction, and that's what we're talking about here, the order of a reaction with respect to any one of the reactants in the reaction is something that has to be experimentally determined.
So there's no theoretical way to determine the order?
No. not really. Now, there may be, the order is going to be related to the mechanism. It's going to be related more to the mechanism. Yeah, so if you know a whole lot about a reaction, you might be able to start speculating what the order is going to be based on how similar reactions proceed, similar compounds proceed in their mechanism. But it's that is the overall reaction. This is what happens. The mechanism is what steps does it go through to get from here to here. And you can't just look at that reaction and know what are the steps in the reaction. The kinetics can give you a view into what the mechanism is. The reverse of it is more true than this relationship. When you do know the order, you can start speculating as to what the mechanism of the reaction is. Okay, rate law expressions must be determined experimentally, cannot be determined from the balanced reaction. It's called the rate law expression, rate law, rate equation. Those are all kind of synonyms for what we're talking about here. Okay, so here's an example of a rate expression or rate law for a reaction. Rate equals K. There's your rate constant times the concentration of A, one of the reactants, to the X power, times the concentration of B to the Y power. So X and Y are the order. So it would be the X is the order with respect to A, Y is the order with respect to B, and the sum of those two is the overall order of the reaction. Important terminology. The order of reaction can be expressed in terms of either reactant, the overall reaction. You have to say what you're talking about. And so here's N2O5 decomposing into NO2 and oxygen. The rate is the rate constant times the concentration of N2O5 to the first power. And probably, I don't know if we have to do this all the time, but in your problems, you might, even if it's a first order reaction, you might want to indicate that. So because the exponent on the N2O5 is 1, the reaction we would look at that and say the reaction is first order in N2O5 and it is first order overall. There's no second term here, there's no other coefficient. So that is a first order reaction in N2O5. Okay, so this is first order in, I guess that's tetrabutyl bromide, or bromo. All right, so what would you call that? Bromo butane. It's first order in this, zero order in that. Here's your rate equation right here. First order in this halogen, alkyl halogen. First order overall. Yeah, so we wouldn't say it's first order in hydroxide. It's zero order in hydroxide. In other words, the hydroxide concentration is not driving the rate. It's just the concentration of the halogen.
So something that's zero order overall, is that just like the rate never changes? I mean,
Yeah, I guess it just has it has a constant rate, and that's very rare.
yeah, I've seen some. Like,
There's very rare that you have an overall zero order reaction, but I have one example somewhere. Final example of the order of a reaction. Here's NO plus oxygen forming NO2. Second order in NO, first order in oxygen. There's your rate equation. These would have been determined experimentally. Okay, we're not just writing that up. This one is a little, not misleading, but it can lead you down the wrong path, because obviously here, these are the coefficients in the stoichiometric equation, but that's pure coincidence in this case. That's very rare, that the order of the reaction is following right out of the balanced equation. Okay, but the point I didn't make. Overall, it's third order. 2 plus 1, it's a third order reaction overall. Second order in NO, first order in oxygen.
Wouldn't a zero order reaction mean it wasn't reacting?
Let's see, if we had a rate equals K times, it would still, you can have a zero order reaction.
it's just a flat line.
It is reacting.
But isn't there a rate? Wouldn't the rate be determined by the slope? And if you have no slope, that would mean there would be no rate. If you have no rate, nothing's reacting.
What would this be? Yeah, I'll have to see.
Rate is the slope, like the rate is the slope of the product, like creating product, right? But K is defining the slope then. Like, you see what I'm saying? Like this is not that graph that you're thinking of when you're seeing like product being produced. This is like rate. So the rate increases as molarity increases, right? It's just saying that the rate does not increase with molarity of anything.
Oh, okay.
But there is a constant rate. So you would, like, if you looked at that graph that you were talking about, yes, there would be a slope. And it would be K.
Okay, that makes sense.
Yeah, okay, so you double the concentration of A and the rate stays the same.
Yeah.
Yeah, but it is rare, and it is something to wrap your mind around. There can be reactions that are independent of the concentration of the starting material. I'd have to dig in my notes here to get the example I saw. Let's see, where are we? Oh, guess what? We're doing really, really good. Okay, let's just take a look at this. Here's kind of somehow the data would come out. So here's experiment number 1 over here. And you're starting out with 10th molar fluorine, 100th molar ClO2, and you find a certain rate. All right, and you're asking yourself the question, what does the rate equation look like for this reaction? So you do another experiment. You hold fluorine constant and you quadruple the concentration of ClO2 and the rate quadruples. So right there, that relationship. Increase in concentration 4 times, rate increases 4 times. So it is first order in ClO2. Third experiment. We're going to double the concentration of the fluorine and come back to the original concentration we had for the first experiment for ClO2. double fluorine, rate doubled. So there's one-to-one proportionality between fluorine concentration and rate. So we end up with this rate equation. It's first order in fluorine. It is first order in ClO2. Okay, let's get this off of here. Okay, now let's just look at that real quickly. One other step. So what we don't know yet, is that. So how do we get K?
Well, if we know the rate and we know the concentration, we can solve for it.
Yeah, you can solve for it. You can, yeah. So we can plug in the concentrations and the rate and solve for K and decide what K is. All right? Just from the data. Now these numbers came out really well. You look at them and the rate is nice and clean and you can see it real well. But if we had to actually do the calculation, we could say that for the experiment 1 that we have a rate is equal to K times the concentration of the fluorine times to some power times the concentration of ClO2 to some power. See, we don't know this yet. So that's experiment 1. Experiment 2, we could do the similar thing. K times 0.1 to the A times 0.04 to the B. We could divide one of those by the other one, and this would cross out, this would cross out, and we would get an equation 0.01 over 0.04 to the B power equals that 1.1 over 4. So basically we got there is 1 over 4 to the B is equal to 1 over 4. So B, not want to write down here, B equals 1. All right, I'm saying we can figure this out by glancing at that data, but if you had experimental data that was a little muckier, you can calculate it this way. We just take 2 of the experiments, divide them by themselves. Given the following one-step reaction as rate law expression, would have to be experimentally determined. Rate equals K times A to the second. If A is doubled, if this were a second order reaction, if A is doubled, the rate is going to quadruple. If A is halved, the rate is going to be 1/4. Okay. Now, this is part 1 homework. Here's what I want you to do. First of all, I want you to do 2 things, just simple little things. Just say this is chapter 20, homework part 1 at the top of it. And put your name on there. And then notice that there, go to the last page, last 2 pages. There's question number 4, and then there's question number 4. So cross out the last number 4 and make that a 5. Okay? And these should be fairly simple. You're welcome to start them now or rush off and work on them later, whatever you want to do. But I'd like you to turn these in on Monday. It's just nothing more than warming you up. This is 20 points of the 100 points of the Chapter 5 homework. These are basic little problems to just determine what the order of the reaction is, determine what the K of the reaction is, etc. Okay? So, any questions? I do want you to read, okay, Grant, you're our calculus expert.
You want that? That's ln of x.
What's the ln of x?
Technically, that absolute value of x. It has to be the absolute, yeah.
See, that I told you he's our calculus expert. Okay, now, here's the standard mathematical tables.
I mean, technically.
Now, you may have the answer to this too, but let's figure out.
That's the question.
It's not plus C.
What does, that's,
Oh, so there's this whole thing that happened in the 80s.
okay, he knows the answer to this.
So I was not told this until I got to college, which I was taught completely differently. A lot of people these days consider log base E and not log base 10, even though there was a designated natural log was designed to be log base E. A lot of people now use log for log base E.
Why?
No one knows why. It's been since the 80s. Well, if we were taught in like middle school, like I didn't find out until I went to college that was a thing. But like everyone always said, oh, log is log is 10. But yeah, no. So you're right. It's just people are weird, and so.
Well, Dr. Crane pulled out his CRC handbook. This is copyrighted 1987. He pulled out his CRC handbook, copyrighted like 1983 or something like that. And it had log, L-O-G. So
LN
yeah.
is more recent or less?
It's older, technically. But like, it's really weird. I don't know why they got rid of it, because then you just have to specify log base 10 versus before it was shorter. It's ln and
But
log.
what Dr. Crane also mentioned is there are some places moving back to the LOG.
You mean log?
And they're
meaning log 10. Oh.
They're meaning
Yeah, no, that's
natural.
what a lot of people do these days.
This?
Which it doesn't make sense at all.
Yeah, I don't know
I
why.
don't know.
they would
Yeah,
do
why?
that.
Like, why? If you have natural log, why do you switch something so it confuses everyone?
Wait, so that is natural log.
Yeah.
Those are the same
log
thing.
is natural log.
Yeah,
Log
log
of
log
E.
base E
And-
is natural log.
So,
Yeah,
like, a lot
log
of times in
base
books
E
and
is
stuff,
natural
It's
log.
that, yeah.
A lot of times,
Yeah.
the first thing you have to do in textbooks is figure out what they are using, if they're using natural log or log for log base E.
Interesting.
Let's write
Yeah.
4 letters instead of 2.
Yeah.
But this is what we won't play around with that too much. But when we get into it on Monday,
Equations, yeah.
we're going to be looking at that integration. Okay? All right. Have a good weekend.